This app is for analyzing data from fluorescent assays that continuously measure thrombin generation in the presence of a fluorogenic substrate. There are several commercial systems for performing these assays and analyzing data, for example the Thrombin. It is also possible to use this app to analyze data from similar continuous assay systems, for example plasmin generation. When the app launches, a set of data from a thrombin generation experiment is loaded, which can be used to explore features in the app and understand what the various settings do. It is worthwhile spending some time trying out the app using these data to understand how to optimize the analysis of your own data. The idea behind this app is to have a system of analysis that can be used on data from a variety of commercial or in-house platforms. This is useful if data from different laboratories are to be compared using a common analysis method, thus focusing attention on differences arising from the assay conditions. Another driver for the app was to present a transparent way of using your own data with selected settings, tuned to your own needs, rather than a black box where data were fed in at one end and results appear at the other. Because the app allows for changes in default settings, it is important to consider what effects your own selections have on the outcome of your results. To begin your analysis, you must first of all load and tune data from your calibrator. The first tab in the app is called Calibrator, and this is where the calibrator data are selected and analyzed, which are applied to correct your raw sample data. I will not go into the theory of thrombin generation assays, or the nature of calibrators, in this video, but more details can be found in the help notes in the link on the help tab of the app. The calibrator curve is shown in the top left of the main panel of the calibrator tab, as the app opens. There are 4 sets of data on this plot. Raw data are shown as black crosses, which begin at a high rate that progressively declines. The decline in rate is due to substrate consumption and fluorescence inner filter effects, and we are trying to correct for this decline mathematically. The correction applied to the calibrator will also be applied to your sample data. There is a magenta line, which is a fitted curve that passes through these raw calibrator points. The next set of data is the maximum rate of fluorescence generation, shown as red circles. The green crosses are a correction of the whole raw data curve that should follow the initial rate. Therefore, the magenta line should follow the raw data points and the green crosses should overlap with the red points of the initial rate. The goodness of fit is indicated by the 4 subplots to the right of the main calibrator plot. I won't go into details here, but you should be aiming for a random distribution of residuals as possible, and a linear quintiles plot. Don't be too concerned if there is non-randomness in these points, which is hard to avoid. You should note that the raw data is changing over 1000 units, but the residuals are fluctuating around 1 unit. In the top right corner, the red line for thrombin concentration should pass centrally through the blue curve. It is expected that the blue line becomes more erratic over time as correction becomes more difficult. Also, in practical terms, you should try to minimize artifacts due to mixing or temperature changes at the beginning of calibrator curve time courses. These can also upset curve fitting. The parameters that are derived from the fitting will be used to correct your raw data. In the box on the left of the calibrator curve are some settings to optimize your analysis. First of all, you need to select the relevant columns of calibrator data. There is a drop-down menu called Curve, which selects the calibrator data to be shown. Included here is also a mean response using all the selected columns, should you want to use this. The input box called Points for Fitting is important and allows you to choose the extent of the calibrator curve. As mentioned previously, large deviations from a linear response become more difficult to correct, so it is advantageous to limit the calibrator time course. However, you should try to include as many points as are needed to cover the fluorescence range observed in your sample data curves. You need to take into account these opposing considerations when you select the number of points in this box. Below these boxes you enter the concentration of calibrator used in the experiment and enter the calibrator maximum rate, which is calculated by the app and shown above the calibrator plot. The calibrator rate and concentration will be used to convert the fluorescent signal into thrombin concentration. Below the calibrator plots are plots of sample data fluorescence time courses. The input boxes here should be self-explanatory. There is a choice of radio buttons here dealing with correction of sample data. Correction is achieved by applying the coefficients from a polynomial fit to a plot of corrected versus raw calibration data. The plots to the right are fluorescence versus time of your selected sample data, and you can see the effect of correction as the red curves, which deviate from the raw data, blue curves. Clearly, correction becomes more important as the fluorescence signal increases. You should take note of the change in fluorescence here and make sure your calibrator curves cover this range. These raw data curves are not very informative as presented here and are transformed into first derivative curves in order to calculate useful parameters that describe the progress of thrombin generation. The final group of settings at the bottom of the left-hand panel deal with these transformed curves and the calculations. The input box of % change for start tells the program that the lag phase is over when thrombin generation reaches 10% of maximum. 10% is the default setting and is typical but may be changed. Smooth tail is the number of points at the end of the curve used to calculate the final level of thrombin alpha-2 macroglobulin complex. You can select a number of points which give a stable final level of fluorescence generation in the transformed curves. This level is used to calculate the kinetics of complex formation. The display options refer to what is displayed on the tabs of transformed curves. These can be best illustrated by clicking on the second tab called Curve. The default setting of thrombin shows the transformed thrombin generation curve, colored to indicate the lag phase in gray, the initial burst of thrombin generation in green followed by inhibitor binding and reduced rate of generation in blue. When this phase returns to 10% of maximum, the curve changes to red and the parameter is called time to tail. After this, the response moves towards its final steady state rate where there is no more thrombin generation and the remaining activity is thrombin alpha-2 macroglobulin complex. The gold curve is the formation of thrombin alpha-2 macroglobulin complex, which is calculated from the thrombin generation curve and the final steady state rate of thrombin activity. If you change the display option from thrombin to F, the plot changes from thrombin concentration to fluorescence units. Note the y-axis changes. There are two smoothing options in display. Smooth tail simply shows the points selected that give the final rate for the thrombin alpha-2 macroglobulin complex. Smooth all applies a smoothing algorithm over the whole curve. While the smooth all function is useful for noisy data, you should note there are some significant effects on the thrombin generation parameters, as can be seen in the table below the curve. The final option is to present the thrombin generation curve with the contribution of the thrombin alpha-2 macroglobulin complex removed. You will have to decide and justify what settings you choose to apply to your data. There is always a risk in providing a number of options for data analysis that the user may select whatever gives the answers they want. It is advisable to think about the best options for your data in advance and stick to a pre-selected set. The third tab on the main panel shows all the transformed curves. Below the curves are radio buttons for choosing which calculated parameter should be displayed. The next tab presents a table of all results, and this can be copy and pasted into other documents as required. Two additional calculations are shown which are lag to peak, giving the time from the start of thrombin generation to the peak, and base, which is the time between start of thrombin generation and start of tail. These may be useful to express the initial burst of thrombin generation and the overall time that thrombin generation was taking place. However, as mentioned previously, it is more honest to predefine which parameters are important in your work rather than do post hoc hacking for the parameters that give results you want. The next two tabs present the raw data and calibrator data being used. These are the data that are loaded when the app launches or your selected data. There are some options controlling the way the data are displayed which you can try out. The Settings tab shows the data files being used and collects the various options that have been applied to your data analysis. This is useful for reproducible analysis, and these settings should be copy and pasted alongside your results. The Help tab provides a brief summary of help and links to more detailed help notes and other apps that may be of interest for hemostasis studies. There are also links to some published papers. I have given my email address in case of questions or problems, and I always like to hear from anyone who is using my apps. In the top right corner there is a theme selector drop-down menu box. You may wish to change the appearance of the app by choosing an alternative theme. I wish you success if you use the app with your own data.